the Newtonium, the uranium, the actinium, practically all the heavies. You see here we had that they are the heaviest in the elements of the table. And here we can, for example, here see a general idea of how is distributed the alpha decay and the beta decay. Yeah, then we had that sometimes this is actually really interesting because sometimes one element is jumping for a new state using alpha decay. When it's in the new state, then it's using beta decay to go into another state, and then after do the beta can be again do alpha to go into another state. Well, then you can have this kind of transition, as you can see here, that you can go to alpha, beta, beta, alpha, depending on what is the stable system. Then all the time they are going to be looking for stability. Yeah, and why we can use this thing, for example, we can use this property to try to see a time dating using lead isotopes. For example, uploads the abundance of the chromium versus the chromium can be sensitive indicator of the age of lead Earth. Since technology has been used to show that meteoritos believed to the leftover from the formation of the solar system 4.55 billion years old. Okay, then the question is why we can use this kind of analysis to understand what had happened before. Because if you remember in the beginning I was talking about one equation that was relating the total number, the total mass, the n, with the time. Then its initial time you have one value, and after time pass you have a new value, you can find the relation between both of them because you have the variation. Then this kind of analysis are giving us information about what happened, for example, 4.55 billion years ago. Then we can understand. This is why we can talk about the past just using the information that we have today. Then it's important because all the time they are going to be continuing in decay after million years. And then they are giving one example that is with the PV that is really one of the, it's going to take a long time, then it's going to give it us information about how everything will happen before. And also the radioactive carbon dating that you know is also used to see, for example, is produced in our atmosphere by bombing nitrogen by neutron and produce the cosmic ray. Yeah, then we have this relation. Yeah, then the nice thing is that it's something that we are find every day in our everyday life, this kind of decay. Yeah, and then we had that when living organisms die, their intake carbon-14 sits on the radio R and decrease in the decay. And for example, 9,000 years ago, then we can see what will happen and relating with what will happen in today's days. Then it's kind of the relation. Okay, I finished this part, but I just like to do a summary just to make sure that everything was clear. Actually, I'm going to ask questions to you. Just okay, quickly. Who like to tell me why we are using the analogy with the liquid role model? Something in general. Would you like to give an example or something? Okay, just quickly, because remember I say in the beginning that, for example, we can begin to analyze what happened inside the nucleus if we do the analogy with the liquid dry water. Because inside the liquid dry water, we had that the molecule had this strong interaction that actually in the nucleus is not the same kind of interaction, because in the water is molecular, in the nucleus is a strong force that is really high, but it's kind of the analogy. This is one. The other is because we have the surface. That the surface here is going to allow this dry water to have this spherical form here inside, yeah, and then you see the interaction close by close. Actually, I also say something interesting about the evaporation. For example, I say if we had the water and then we had evaporation, you are going to be losing the water. And then you are going to be emitting, when you are close to the kitchen and you have hot water, you feel that it's hot, no? Then it's similar with the decay. It's not the same. It's the analogy with the decay, because in the decay you are going to be emitting radiation. Obviously, it's not the same, but it's kind of the analogy. This is why this analogy is working, because if you have the water and you put hot temperature, then you can feel the hot coming in your face. If you stay there, you feel that you are going to burn. But then in the decay particle, you are going to be having the emission of sun ray. And the other thing is the condensation of the liquid, because in the condensation process, then you are going to add something. Then in this case, in a nucleus, we are going to be adding, for example, electrons to make the system more stable. Then this is why the analogy is working. It's like an analogy that scientists were using sometimes to explain in more kind of clear way how can happen, okay? Okay, I hope now it's more clear, okay? Let me ask you another question here. Okay, this is what I was talking about, the radiation decay, that we had the relation with the time. And actually, now that we study the carbon decay and everything, you can see how this relation is working. Because it's today that is so many billions, we had information about how much we had and about, for example, 1% of some substance. We can find information about how much was before, because we know that how much time are being passed, and we had also this constant that is giving information about the material. Then this relation can be giving information about what will happen so many years ago, or you can have information about what is going to happen later. If you had some, this is why people also are worrying when a nuclear explosion happens, because say, oh my God, it's not radiation that is going to end in tomorrow or in 10 years. It's going to be longer, because it's going to continue decay. And then if you do this calculation, you are going to see that so many years later, you are going to still feeling the impact of the radiation. This is how it's also dangerous, not only in the moment that happened, but later. It's going to be dangerous for the nation, for the people, for the genetics, for everything. Then this kind of analysis shows the consequence also. Okay, here then we have the different kinds of decay, and then I'm going to ask question. If somebody remember, can somebody tell me about the alpha decay? Something. I see that some people, huh? Yeah, you have the emission, and then you are trying to lose for a stable state, then you are going to lose the helium, and you are going to also lose 2 protons. Yeah? Then you are going to go in a more stable system that is going to have less protons, less neutrons, but you are going to have an extra helium. But if you're thinking, the helium is not dangerous, because helium is something that the sun is having helium. Then if you're thinking in energy, for example, a good way to do clean energy is, for example, to use the alpha decay. Because actually the thing that is going to waste is going to be helium, that is not dangerous. It should be nice is actually the technology in the future can kind of reduce the expense of the clean energy, because as you see, it's not dangerous, it's not having, this kind of radiation is not dangerous for us, not dangerous for the nation. But today it's super expensive to do it. Then this is why people are not really that much interested. But hopefully in the future can be. Okay. Now let's see about the beta decay. everybody like to say something, but everybody else
Protons or neutrons, nucleus, and it turns like neutrons into protons or protons into neutrons by inhibiting or by giving off an electron or a positron.
yeah. Yes, exactly. This is what happened. Again, trying to look the stability, then you are gonna turn neutrons in proton or protons in neutron, and as consequence for the conservation of energy, you are gonna have an extra electron and or a positron with the highest speed. But also remember that later we say that also we had some neutrinos that doesn't have charge. Yeah, then is another way. Then the interesting thing is that we can also pass to neutron to proton, proton to neutron, and then the electrons are gonna be moving fast. Okay. Okay, electron factor.
So this is when the nucleus captures an electron and one of the protons turns into a neutron and a neutrino ejected.
Yeah, in this case, then, as I tell you, in the other case, you were sending something out. In this case, we are going to capture, like you say, one electron. It's going to be part of the nucleus. But as consequence, then you are going to have that the number of neutrons and the protons is going to change, and also you are going to have one electron inside. Then, and this is the opposite with the other two. The other two were sending things out like, oh, I don't like this door. But this one is like, no, give me because I like a stable system. But everything happened in looking for stability. All the time nature is trying to look for stability, sometimes trying to send in out neutrons, protons, other time trying to capture electrons. Yeah, but all the time you are sending extra energy to have the conservation of the energy that you were having in the beginning. Okay, the gamma decay. And how the gamma decay is different with the other kinds of decay.
It's just the hydrogen photon released from the nucleus.
Exactly. This time we are not going to change this. We are not going to transfer something in something else. We are going to just lose energy. Like we are in a high exciting state, and then it's going to go down, down until become more stable. Yeah. And then we talk also about the metastable system. Who can tell me how was the metastable system? Or one example?
It's one that decays at not at a sharp rate, at a very sort of steady rate.
Yeah, then you are going to be in some state for some time, and then after that you are going to decay. Because we had the forbidden jumps sometimes, like you cannot just go directly to the stable state. Then you need to stay until you, mostly as you say, you are losing the energy smoothly, until you had the difference. This means when you had when you had the perfect variation of energy to do the jump that you like to do. Okay? Who like to tell me something about the radioactive carbon dating or the lead isotopes and how we can use this to do analysis about what happened in some many years or what is going to happen?
Jeff. The lead isotopes are going to disappear over time, and you record that. You can tell how old something is.
Okay, then we can.
So it's going to lose mass. It's going to lose mass over time, turn into something else. You can measure that. Seems to be the only thing I can think of. Hey, you know what its half-life is, so you can measure it pretty accurately over millions of years.
Yeah. That's, actually, that's a good point, because if you had information about how much you had about some substance, then you can use the relation about the decay and try to see how much is gonna be in the future or how much was in the past, and have some relation. And this is how you can use this thing for dating and take some data about what is happening. Okay, and the same thing, I don't know if somebody like to say something about the carbon dating.
It's just that it's more based, that, the lead was based on inorganic, and I guess this is based on living organic organisms. So instead of looking at carbon, instead of looking at lead, you're looking at carbon and its ratios. Really, it's the same principle, just a different molecule.
Yeah, and in this case, for example, we had that the neutron plus the nitrogen, for example, is gonna give us the carbon-14 plus the proton. And then we can see what is happening in years, for example, 9,000 years ago, that the ratio was different. Okay, somebody had any question? Okay, then we finish for today. Okay?